final speaker for today is in fact myself. I'm Dr. Kaye Morgan, also from the School of Physics. In 2011 I completed my PhD here at Monash and was awarded an ARC Early Career Discovery Researcher Award, which has allowed me to continue the research that I began during my PhD. My research focuses on new ways to capture and interpret X-ray images with a focus on soft biological tissues and also on high-speed sensitive imaging. The majority of my experimental work has used X-rays from a synchrotron. I've been lucky enough to visit the Spring 8 synchrotron in Japan 17 times over the last couple of years, which is great because I love to travel. I also love to take photos, not just with X-rays, but also with visible light. So the talk that I'm going to present to you today is titled Playing with Light from the Swimming Pool to the Synchrotron. Okay, so we're going to start by talking about X-rays. So if you think about an X-ray image, you probably think of something like this. So a bone, or you put your knee in front of an X-ray wave field, the bone's absorbed some of the light, and so we get what is effectively a shadow image. So if we got this film and actually developed it into a photo, we would see something that looks quite similar. There's not so much light, or it's darker, where the light, the X-ray light or the visible light doesn't get through, and then it's brighter around the edges where the light's getting through either air, or in the case of X-rays, the soft tissue that surrounds the bone. So this is great if we want to image something like a bone which casts a nice strong shadow. But what about if we want to image something which doesn't cast a strong shadow, like some soft tissue, so muscle or fat or the lungs or something like that? Or by analogy, we could say that a glass of milk will give us a nice strong shadow, so we could easily see how full the glass was. But if we had something like a glass of water, we don't get a very strong shadow from it. So I'm going to continue with this visible light analogy and go to an even larger volume of water in a swimming pool. So what if I was to challenge you to figure out what the shape of the water is in the swimming pool, just like we'd work out what the shape of the bone is inside the knee. So we're not seeing any shadows from the water because the light is going straight through the water, but we are seeing some interesting patterns here. So the first way we could do it is to look at these white lines that we're seeing on the bottom of the pool. And so the waves in the pool are effectively acting like a whole lot of lenses which are focusing the light into these patterns. And there's actually a really interesting whole field of physics in terms of the caustics and the particular shapes that they make here. So we could look at those white lines. We could work out how they're created using some maths like this to describe the behaviour. And in fact, we have just in recent years had a new method of X-ray imaging called propagation-based phase contrast imaging, where we effectively do that kind of thing. We let the X-rays propagate an extra metre past the patient, and we see that we get all the little air sacs in the lungs acting like a whole lot of little lenses, just like the waves acted like lenses in the swimming pool. And so we can see a whole lot more detail in something like the lungs here. So this works really well when we're comparing air and tissue. But if we want to look at one soft tissue compared to another, so muscle from fat in a single image, this starts to reach some of its limits. So let's go back to the swimming pool. If we also look at this image here, you can see there's something else interesting going on, and that's the shape of the tiles on the bottom of the swimming pool. So if we zoom in, you can see that those tiles are distorted by the waves in the swimming pool. So the light's going through the water, but it's changing direction, and so that we see these kind of distortions of the lines. So we could actually analyse this pattern, what those tiles look like, to discover the shape of the water. So let's draw a diagram. Physicists like to draw diagrams to explain how something's working. So we've got a whole lot of tiles here along the bottom of the swimming pool. We've cut the pool in half, so this is in cross-section. We've got some waves here with some water. So if there's light coming up from the bottom of the swimming pool, we're going to see that it goes faster through the air than it does through the water. And so we start to get these variations in the phase of the waves that are coming up to our eyes. So if we drew some lines coming from the grout lines between the tiles, we would see that some of them are going to start to bunch together and others are going to look like they're further apart. So we're going to see these distortions to the tile patterns. So let's get this diagram and we're going to put it on its side and replace the water with soft tissues. So now we're going to talk about X-ray light instead of visible light. So when we're using X-rays, there's going to be a few differences. First of all, the angles that they change going through a sample are going to be much smaller, so we need to go a greater distance to see that same kind of distortion. We're also going to see that they're going to bend or change direction. The refraction is going to happen in the opposite direction to what it does going from water to air with visible light. But apart from that, we're going to see effectively this same kind of behaviour. And so this setup is in fact what I've been working on for the last couple of years. We call single grid phase contrast X-ray imaging. So we place a single grid in front of the soft tissue that we would like to image. So this is the grid that we've got here. We place a camera to collect the image at the far end, and we illuminate the sample with X-rays from a synchrotron. What is a synchrotron, you may ask? Here's a few synchrotrons that I've done some work at. They look kind of like a UFO. And they're big research facilities. And what happens is there's electrons that are passing around inside a vacuum tube. There you go, 1 million times around per second. So this is slightly slowed down so you can see them. And every time the electron turns a corner, or if we use some magnets to make it wiggle, it's going to give off light. And so we have this happen many times around. So there's a little workstation or experiment happening at lots of places around the synchrotron. If we go inside, it might look something like this. This is the Swiss light source, so a really big hall. And then we've got the electrons are passing down inside this particular ring here. If we're going to go down to the ground level, you'll see that there's areas where we have radiation, and there's areas where we have the scientists. So we have really nice thick lead shielding in between to make sure that the radiation dose isn't too great. We might have it set up something like this. So you notice it might look a bit messy. This is usually because we only have a couple days in which to set up the whole experiment, collect all our data and completely disassemble it. So sometimes the duct tape does come in handy. So why are we using a synchrotron? There's a few reasons. The synchrotron is really bright, so it produces, what we can do is get rid of all of the wavelengths except for one, so that we just have a single wavelength of light and we'll still have plenty of light, which we wouldn't with a conventional X-ray source. It also has a beam with really low divergence, so they're all kind of heading in the same direction, the light, which means that we can go quite far away from the source and still get plenty of light. So where we do the medical imaging experiments, we're actually out this tunnel here, a building somewhere over here at the Australian synchrotron, and we're way off the end here at the synchrotron in Japan. And that's so we can get really high coherence. So we want these wave fronts that are coming into our experiment to have really uniform phase as they're coming in. So just to explain this, I'm going to show you a little analogy of some ducks. So we can say that the electrons that are going around the synchrotron, they create the light. These ducks are going to represent our electrons. They're going to jump in a pond and create waves. So they're waves in water rather than light waves, but the same principles are going to apply. So you've got this bunch of ducks, they jump in the pond, they create some waves, and you can see where they've just jumped in, the waves are really kind of choppy. They're all over the place. You don't really have any nice straight wave fronts. But if we move quite far away from the ducks, you can see that these wave fronts are nice and uniform in phase. They're quite close to a plane wave. And so that's giving us nice coherent light. So we want to go nice and far away from the source so that we get really coherent waves. Similarly, you could say if we just had one duck jump in the pond, then we'd have nice waves nice and close to him. And so we also like to have a really small source size, so the electrons are in quite close together, so that we get nice coherent radiation. So that's why we hang out far away from the synchrotron. It's not because we're antisocial and don't like the other scientists, it's just so we can get some good coherence. So we can illuminate a grid. We've got a grid pattern here illuminated by the synchrotron. And if we place some disturbances in the way, so this is kind of like the swimming pool without any water in it. If we place some water in there, or if we place a couple spheres in the way, we see that the pattern is slightly distorted. So there's a big sphere up the top here and then another one down here. And you can see if we're outside the spheres, it's not moving at all. It's like having some water that's still in the swimming pool. But where there's quite a kind of sharp change, as we go near the edge of the sphere, like a really kind of big wave in the swimming pool, we see quite a bit of distortion. So it's pulling the pattern across this direction, and it's also pulling it down near the bottom of the sphere, and then kind of a diagonal halfway in between. So what we can do is we can look at how this pattern is being distorted, and if we say, okay, how far is the pattern being shifted locally in the horizontal direction, we'll get something like this. So shifts of a few microns with 1 metre propagation, so very small angles, like I mentioned earlier. And then also in the vertical direction, so it was getting pulled down quite a bit in terms of that local part of the pattern there. So we can get these differential contrast images, which are describing the derivative of the phase of the wave field after it's gone through that soft tissue or the sample. We can also combine these with some knowledge about our experimental setup to get the thickness of the sample, so we can know exactly how many millimetres thick it is. It's much more interesting if we have a nice fine grid, and also if we have a really a more interesting sample. You're seeing some Moira effects here. There's actually a really fine grid on top of there, and depending on the sampling, you can kind of see there's actually, looks like there's some big lines there. So we can extract from that the differential contrast in the vertical direction, in the horizontal direction. We can get the thickness from that. We can in fact just get rid of the grid and look at the, that edge enhancement that comes with propagation. Or we can look at how the pattern is decreased in visibility due to the structures that are even smaller than the size of the pixels themselves. So we've applied this to image the airway surface, placing a grid on top of the airway here. We can see the airway and the tissue in the reconstructed image. And we've been using this to test new treatments for cystic fibrosis. So in cystic fibrosis, this liquid layer here, you can see there's a really fine line going down between the tissue and the airway. And so there's liquid in this little space here. And that liquid depth is decreased in cystic fibrosis. So if we have an effective treatment, we want to see that increase so that any debris that lands on the airway surface glides away from the lungs. And so we've imaged and tracked that, and we've seen that we do get an increase with an effective treatment, which is quite exciting as the first non-invasive measurements of the local airway surface health. So just to finish off, I thought I would show a quick movie to say that we can also visualise the airways in 3 dimensions, not just in 2D, and we can explore them in software going from the nose here, right down through the back of the head, through the trachea, which is the main airway through our neck, and down to the lungs. So you can see branching off to the 2 lungs there and all the smaller airways going out to the periphery of the lungs. That's it. Thank you.